Hey there, man, Alejandro. Welcome back for day 282 of me doing daily LeetCode challenge after reach 1 year's worth of great contributions here on GitHub. Today's one is for April 24th, 2025. Without further ado, let's get straight in. Okay, today we get a LeetCode medium from 27.99. Count complete subarrays in an array. Okay, seems like LeetCode hasn't been getting enough of these counting problems lately. Okay, you're given an array nums consisting of positive integers. We call a subarray of an array complete if the following condition is satisfied. The number of distinct okay, given an array nums consisting of positive integers, subarray of an array complete if the following condition is satisfied. The number of distinct elements in the subarray is equal to the number of distinct elements in the whole array. Okay, return the number of complete subarrays. Wait, this is actually kind of easy, right? Printf string distinct count. Yeah, 3. Yeah, this is just going to be classic. Yeah, this is actually going to be really easy. It's a counting problem, but thank goodness this is not combinatorics, although I now know the stars and bars method, kinda-ish. That might help me in some of the future counting problems, thanks to @Riri, I believe it's Riri519 is their username. So shout out to Riri. I still haven't seen the new comment. Well, I've read a bit of the new comment, but that is a long comment, but juicy information for me to learn from. So thank you for helping me learn combinatorics. Okay, yeah, this is just going to be classic sliding window. So here we're going to do L is equal to 0 for R in range. R, num, and enumerate nums. Let's add the number to our current dictionary. So here we'll have this. D of num is equal to d dot get num, 0 plus 1. While length of d is equal to distinct count. Here we'll say res is equal to 0, res plus or equal to 1. Here we'll need to do an L plus or equal to 1, but first we're going to delete the thing at index L. Here we'll say num L num is equal to nums at index L. D of d dot get num minus or equal to 1 if d of num is 0, del d of num. So it'll be minus R, I believe. And then return res, so like this. I might need 1 at the very end, maybe not, so we'll see. Okay. Is there an ending one? Yeah, this is an ending one, right? So here I can just do something like this. Although n minus n is going to give no results, right? Res plus yeah, this actually should be enough. Yeah, here I'm still going to be wrong. Yeah, I should actually still be wrong here. This should actually be enough. Yeah. Interesting. It's not an n minus r plus 1 type of thing, right? Nope, not at all. print f string numbers from L to L plus 1. Because now I'm going to print the valid subarrays that I'm considering here. Nums from L to dx plus 1. Okay, so I'm considering 13112, 13122, 3122, even though 312 has 1. Okay. Okay. Right, what's the time complexity? Ooh, num's length is 1,000. Well then, ladies and gentlemen, there's a much easier way of going about this, right? Ooh, damn, my shirt is broken. Okay, well that's good thing. Okay, you can't see it from my angle, I can't see that, but okay, on the video I can see that it's, well, I didn't even know my shirt was broken. Holy crap. Okay, that's a cool thing to know. Yeah, so the fact that this is 1,000 means that we can actually do n squared time, or in the worst case, actually use a segment tree for something like this, right? We want to range. Because really what I want to do is, okay, then, but somehow incorrect, but incorrect. Not somehow, just but incorrect. Right, here I want to do dp self, I, if I, self.distinct, distinct count, square equal to set.n is equal to n. Okay, sorry about that. I think I accidentally hit Command-Shift-J, which opened up my downloads folder on Brave, which I don't want to show, so sorry about that. Yeah, here I was just doing this. Okay. Okay. Get rid of this guy. Yeah, here we can just do for I in range. Distinct is equal to set. distinct.add. Here we'll say distinct.add what? Here we can even just do this. Which is a little slower, but it'll be at least correct. Yeah, I can go to this now. Okay, I'm starting to lag a little bit on my computer. Holy crap, oh my gosh, I am lagging hard. Okay, please stop lagging. Okay, jeez. Oh my gosh, I am lagging really hard. Okay, fine range, well that would be why. Okay, so something like that is accepted, and by the constraints here, it should just be passing. Okay, there we go. Completion streak 282 days, consistency is key. See you tomorrow. Okay, so is there, yeah, okay, so there's a huge peak over there, which makes me think, yeah, there's definitely an O of n, row of n, log n way of solving this, right? Here we can definitely do things a little bit better by doing this. Holy crap, is this slow though? Yeah, so this also works, and we should do a lot better than 728 a mess. So now we're at 507. But yeah, okay, so there is indeed, dude, it is crazy how much lag I have. I hope I just don't freeze, that's all I care about. Of n squared solution. But yeah, so my off the bat intuition was to do an O of n thing. Now I gotta figure out why this guy's just not correct. So the problem is something like this, not distinct, not distinct, not distinct, finally distinct. Yeah, should be getting rid of the left here and still have the 3, 1, 2. This doesn't make sense. This should be working. Wow. Okay, so I'm not accounting for length 1 here. Yeah, so I guess L can go 1 more. So what's happening? I'm gonna go here, not distinct, not distinct, not distinct. It is distinct, right? So finally. Then yeah, I'm printing the rest of the array. So I did this, and I'm gonna cut off L. And this is indeed distinct. This should not be this should be completely fair. I should be deleting 1 here, which was a frequency of 2. D equals. What in bloody tarnation is going on here? Oh my gosh, I'm not doing LNum. Nah, that's actually crazy. Yeah, okay. That's just a typo on my end. But yeah, okay, output limit exceeded. It is crazy how much I am lagging. Oh my goodness. Okay, so here we'll say res comma L comma D are equal to 0 comma 0 comma this. Oh, then dude, I'm lagging hard. I'm lagging hard. Okay, there we go. 11 ms beats 78.5%. Yeah, so this is the very first solution that came into my mind as soon as I read the problem. It's just I was like getting like, you know, wow, what's going on here? Yeah, this makes a lot of sense. So after reading the constraints, I was like, oh wow, an O of n squared solution will work here, but yeah, that's just absolutely not needed. But holy dude, I'm actually lagging so hard. Like LeetCode should not be something that lags this much. Okay, so you know, before my computer explodes or freezes or something, I'm just gonna get straight into the solution explanation. So nevertheless, as always in all my videos, I do a quick recap if I was able to solve the problem. So this one, we want to count the number of complete subarrays in an array. What does it mean if an array is complete? Well, get the total number of distinct numbers in nums, and you want to count how many subarrays has at least one instance of each unique number, right? So for example, this nums array has the numbers 1, 3, 1, 2, 2. So the distinct numbers are 1, 2, 1, 2, and 3, right? So now you want every single subarray that has at least 1, 1, at least 1, 2, and at least 1, 3, right? So for example, 1, 3, 1, 2 has at least 1, 1, has at least 1, 3, and it has at least 1, 2, right? So this is a valid array, right? But something like just 1 isn't valid, right? And so like here, 1, 5 is indeed valid, right? Because there's only one distinct unique element, which is 5, and so an array even of length 1 with just 1, 5 is valid. So is like, you know, so is this array, so is this array, and so is this array. In fact, every single subarray of nums here is actually valid, right? So the very first thing that I did is like, okay, let's grab the length of nums, but more importantly, let's grab the number of unique elements, right? The distinct count, which will be convert nums into a hash set, so that way you only get the unique values of nums, and just grab the length of that. That'll be the total number of distinct elements in nums, right? Then you essentially want, what I did is, well, first of all, the constraints allow you to do an O of n squared solution. So if you really want to, you can do an O of n squared solution, and this isn't too hard to understand. Essentially, for every single index I in nums, find how many there are complete subarrays that start at index I, right? So it's like essentially grab like, you know, a hash set of all the numbers in your current subarray. So for every single subarray starting from every single index I in nums, here's like, okay, let's go from j index I to n, and let's keep adding a number. And if the length of the current hash set is equal to distinct count, then, you know, we're gonna add all the remaining possible subarrays, right? Or even better yet, what we can do is instead of breaking here, we can just do you can just do res plus, here is just like, if length of the distinct is equal to distinct count, you can just do res plus or equal to 1, right? And something like this will technically work, right? But this is the easy, naive, trivial solution. And if I submit something like this, you will see that it indeed works, right? Because the constraints of this problem allow for it, but there is definitely a much better way of going about things. So I'm just going to delete this O of n squared solution and just leave this O of n solution right over here. Okay, just have to make sure that I'm not freezing my screen. Oops. Okay. my computer is very laggy right now for some reason. I don't know what's happening. Okay, 7ms beats 95.10% of solutions. That's very good. Okay, I'm just going to try to finish my explanation before my computer absolutely explodes here. Okay, so here I have res is equal to 0. We have a left pointer is equal to 0, and d is equal to the hash map. What's going on? Let's do a sliding window, right? We don't have to actually do n squared. Here we can just do a sliding window, and every time we reach a valid solution, right? For example, let's say we reached our very first subarray. So here's like we have 1 1, 1 3 and 1 1, 1 3 and 2 1 and 2 1s, 1 3 2 1s and a singular 2. Okay, this would be a valid subarray, right? Now once we reach a point that is a valid subarray, what we can say is like, okay, how many valid subarrays are there that start from index 0? Well, we know that this is valid, right? So we know that adding any more numbers will also be valid, right? If our current window has all the distinct numbers, then we know that no matter how many more numbers we add to the window, it is still going to be a valid subarray, right? Because the more numbers we add doesn't remove any of our distinct elements in our current subarray, so therefore it must still be a valid subarray, right? So here what we're doing is we start from L is equal to 0, and we're going to keep adding nums into our current sliding window subarray, which will mark each number in our current. So instead of having a list of all the numbers, we'll have a hash map which will map numbers to their frequencies, right? And so whenever the length of the hash map is equal to the total number of distinct elements inside of nums, which are computed over here, that means we have every single distinct number in nums. So it's like, okay, we have a valid subarray. We know that no matter how many elements we add, it's still going to be a valid subarray. So what we're going to do is, while this is still the case, we're going to say, okay, res plus or equal to n minus r, right? Because there's n minus r last indices that work for this, where L is our current left index, right? So for example, here, right, R would be 0, 1, 2, 3, index 3, and there's 1, 2, 3, 4, 5 elements, right? So 5 minus 3 would give you 2. Why? Because starting from this index, this is a valid index, and this is a valid ending index, right? So this subarray, as well as this subarray, are valid subarrays, right? But since we know that this is valid, we know that adding another 2 doesn't do anything, our subarray is still valid, right? Because it's about the number of unique elements in there, not the total number of elements or anything like that, right? So that's why we do res plus equal n minus r. And here we've solved the number of valid subarrays that start at the current index L. So let's move our sliding window by shifting the L pointer by 1, right? So let's grab the number at index L. Let's decrease the frequency of that number by 1. And if the count is now 0, then that means we no longer have this element, so we'll delete that from the hash map and obviously increment our left pointer, right? So here what's going on for our num and enumerate nums, we're going to keep adding, like, okay, we're seeing this number, so let's augment the number of times I've seen this number by 1. So d of num will be get the frequency of num, or 0 by default, and add 1 to it, right? Then while my current sliding window has all the distinct elements, right, while the length of the hash map is equal to the distinct count, let's do res plus or go to n minus r, because that's how many valid subarrays there are that starts at the current index L. Update the index L index, and obviously when we subtract the frequency of the number at index L, and we subtract it by 1, then if it's 0, that means we no longer have that number, so delete it from hash set, which will make this while loop condition false over here. But as long as that's happening, just L plus equal to 1, always adding to res and so on. And then once we've exhausted through this entire for loop, then we'll just return res, which will have the count that we want. And as we can see, this is a nice, beautiful, and efficient solution. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful and enjoyable in any way, shape, or form, I'd highly appreciate if you left a like or comment. But otherwise, I'll catch you next one. So till then, ciao, ciao, my friends. Bye-bye.